All right, we have three completely different kinds of physics that we're using this week. So, one of the most important things we have to do for each problem is decide what physics we're going to use to solve it. So, let's look at example number one. A uniform thin rod with a length of 2 meters is supported by an axle on one side. It's dropped from rest from an initial angle of 30 degrees below horizontal. What is its initial angular acceleration, and how fast will it be rotating when the rod passes vertical? All right, so our first challenge in any of these problems is to figure out what physics to use. And we've got three choices. We can use Newton's laws, which we are adding some extra stuff for rotation. We can use conservation of energy, which again, we're adding some extra stuff for rotation, or we can use conservation of angular momentum. Now, if we want to determine the angular acceleration or the acceleration of an object, we pretty much have to use Newton's laws, because only Newton's laws deal with acceleration. Conservation of energy and conservation of angular momentum deal primarily with how fast it's rotating, omega. So, for part A of this problem, we're going to need to use Newton's laws. However, for part B of this problem, we want to find out how fast it's rotating when the rod passes vertical. So, should I use conservation of energy, or should I use conservation of angular momentum? Now, this seems like let's see. If I want to use conservation of angular momentum, then what I'm looking for is an object that's isolated that sort of changes shape, so its moment of inertia changes. If I'm wanting to use conservation of energy, then I'm looking for a situation where an object's gravitational energy changes or its spring energy changes, so that its kinetic energy can change. So in this case, the object is basically falling towards the Earth, so it's losing potential energy, which means it's going to gain kinetic energy. So I'm going to use conservation of energy for part B. All right, so for part A, we're going to use Newton's laws. For part B, we're going to use conservation of energy. And there's just a lot of stuff happening this week. It is, in many ways, the biggest quiz of the semester. It is also, in many ways, a review of what we've done all semester, because there's really nothing new here. We're just doing the same stuff we've done before, but with rotations. All right, well, let's take a look at part A. For part A, we're going to need a picture equation. So let me redraw my rod with my hinge. And now I need to determine the forces on the rod. So, of course, we have gravity, which pulls from the center of mass. And because there's a hinge, we can have a hinge force that puts it in the y direction and a hinge force that goes in the x direction. All right, and last week when we were doing statics, that was it for our picture equation. But this week we want to finish the equation by saying that this is going to equal I alpha. That is the moment of inertia times the angular acceleration. And what I want to do with this is indicate the direction of the angular acceleration. And this object's going to rotate in this direction, and it's going to speed up, which means the angular acceleration is going to be going this way. So we're going to make this the positive direction, because it's just easier to make the direction of the acceleration positive. All right, so there's my picture equation. Uh, the forces are indicated on the object to the left, and the I alpha is indicated on the right. And we are going to be using the idea that if we add up all of the torques on this rod, it should equal the moment of inertia of the rod times the angular acceleration. So we need to find all the torques. Now, one difference between statics and dynamics when things are actually moving is that we don't get to pick any axis of rotation we want. We have to choose the axis of rotation that this thing's actually rotating about. And this thing's actually rotating about the end over here with the hinge, so that has to be our axis of rotation. All right, so we've got three potential torques: the torque from Hy, the torque from Hx, and the torque from the force of gravity. The torque from Hy is 0 because the lever arm is 0. The torque from Hx is also 0 because the lever arm is 0. And for gravity, we need the lever arm, which is going to be half the length of the rod. Okay, the lever arm is the distance from the axis of rotation to the place where the force acts, and that force is acting at the center of the rod. Okay, times the force of gravity times the sine of the angle of the torque. And the angle of the torque is going to be this angle right here, the angle between the lever arm and the force. And what we know is that this angle is 30 degrees. So the total angle we're looking for is 30 plus 90, or 120 degrees. Okay, so those are my torques, and that should be equal to the moment of inertia times the angular acceleration. Now I'm going to go ahead and put in my moment of inertia. This is a thin rod rotating around one edge. A uniform thin rod rotating around one end. And so I go and look that up. Let's see if I can do that here. So a rod pivoting at one end, this equation says that the formula should be 1/3 ml squared. All right, so my moment of inertia is 1/3 ml squared times alpha. And now we are ready. I really shouldn't use a different symbol here. I used a lowercase l for the length of the rod on the left. Let's continue to use a lowercase l for the length of the rod on the right. Okay, so now we can solve this thing for alpha by dividing both sides by the thing in parentheses there. And I get alpha is equal to L over 2 mg sine of 120 degrees, whoops, divided by, that's a L over 2, mg sine of 120 divided by 1/3 ml squared. And I notice that my masses cancel, which is nice because then I don't have to plug in mass. One of my L's cancels, leaving just a 1/2. And it looks like that's all the canceling I can do. So I get 1/2 times 9.81 times the sine of 120 degrees divided by 1/3 times the length of the rod, which was 2 meters. And that gives me an angular acceleration of 6.37 radians per second squared. Okay, I'm going to go ahead and pause, and we'll do part B in the next video.